Okay, picking right up from the previous video, which covered Laplace transforms of just functions, we're going to go ahead and do Laplace transforms of derivatives now, and see if we can figure out a pattern so that we don't have to crunch through the arithmetic every single time, or the math calculations every single time. So this is where we left off last time. Our solution was of this form for this specific differential equation. This is an ordinary differential equation. Once again, we're looking for a solution y of t that satisfies this, and we're going to do try Laplace transforms to come up with a solution here. Notice that there's an initial condition given that we didn't really talk about last time, which we'll try to apply this for this scenario here. So we have at this point established what we have: a 3y, capital Y, and that stems from taking the Laplace. Just in general, I should review this. Laplace of a y function is going to give you a capital Y. Notice this little y was a function of t, and this is going to be a function of s now. I could have had anything as a function of t. I could have had a Laplace of f of t, and that would give me, let me see if I can write this a little bit better here. That would give me a capital function f, and that should be a function of s. Once I do the math calculations that the Laplace transform is defined as. So going to this here, we're going to do the same thing, a similar thing I should say, on the derivative of dy dt, and you carry it out the same way. We're trying to write this as some big function of y. And you do carry it out the same way. What I mean by that is Laplace of dy dt will be equal to the integral, and this is just using the standard definition of Laplace transform, e to the minus st. Instead of writing dy dt, I'm going to go ahead and write just y prime of t, and that's dt. How would you solve this? Hopefully you would think of using integration by parts, where u is going to be equal to e to the minus st, and u prime is equal to minus s e to the minus st, and v prime is going to be equal to y prime of t, and if that's the case, then v is going to be equal to y of t. Now, using that, once again, integration by parts, we go ahead and plug in, well, u times v, that's going to be equal to, I'm going to simplify here a little bit, y of t over e to the st. All I've done here is I multiplied these two, and I wrote this in the denominator with a positive exponent, and that's going to be evaluated from 0 to infinity minus integral 0 to infinity of it's u prime times v, which will wind up being equal to minus s e to the minus st times y of t dt. Focus on this first term here and go ahead and expand that and evaluate that as t goes from 0 to infinity. That turns into, I'm going to go ahead and write the limit as t goes to infinity of yt over e to the st. Now this is all the first part, minus, we can call this y of 0 over e to the s times 0, which is, we know is going to be 1. And then I can pull this negative and pull the s out as well, because that's treated as a constant with respect to t. So this winds up being plus s integral 0 to infinity e to the minus st y of t dt. Now let me just reestablish here. We're trying to figure out what happens to the Laplace transform of dy dt. How a dy dt is actually transformed in terms of a Laplace definition. So this can be simplified by saying, as the limit of t goes to infinity, you have a y of t function. Once again, you have a t function up here that's going to go to infinity, but this exponential is going to explode. The exponential function down here will actually take this. We can say that this will goes to 0 as well. There are some assumptions perhaps we can discuss about this, that we can say that yt cannot be, but let's just, for now, just say that it doesn't matter what y of t is. This exponential e to the st will wind up overtaking eventually this function that we have up here of t. So With that said, yeah, that goes to 0, and what you have here, and I want you to notice this is going to be 1, of course. So this is minus y naught, minus y of 0 over 1. And this right here winds up being s multiplied by, this winds up being the Laplace transform of y, which is just written as big Y of s, or just big Y. So what this whole thing simplifies to is, I'm going to write this first here, is s with a big Y minus y of 0. So this right here is equal to the Laplace transform of dy dt. Now that said, the way this would work is I would take this right here and plug that in to the Laplace transform here. So what this whole thing winds up turning into is sy minus y of 0. That right here is your first term here, plus a 3y equals 13 2 over s squared plus 4. Now we have big Y's. We have a y of 0, which we know, by the way, is given up here as a 6. So we can say sy minus 6 plus 3y is equal to 13, or I could even reduce this, I should say, to, or simplify this to 26 over s squared plus 4. So this is what I meant earlier by the algebra. I can now, this is my big Y equation. It's a Y as a function of s. I can move the 6 over, and this will turn into 3 plus s big Y is equal to 26 over s squared plus 4 plus 6. And now, once again, the algebra continues, and I can say that this y of s function is going to be equal to 26 over s squared plus 4 plus 6, and this whole thing is going to be divided by 3 plus s. Now, I want to stop here with this problem before we go on any further and say this winds up being just an algebra problem now, where these are all little s's, and once again this is a y function as a function of s, but understand that this right here is really the Laplace of y of t. And I'm saying that because that's what this, don't lose sight that this big Y of s is actually the Laplace of little y of t. And I went ahead and actually, that's kind of what I'm saying up here. Why is that important? Because if I wind up ultimately looking for a function y of t, I can undo this Laplace by taking the Laplace inverse, which this is what I want to talk about in class tomorrow. But if I do this to this side, then I would have to do the Laplace inverse to this side, and my answer would wind up being just y as a function of t equal to something. And we'll go over what the actual response is for that on the next lesson. So that said, I just want to cover one more thing and to try to figure out a pattern here, because we did dy dt and we did the Laplace of this. Let me actually write that as Laplace here. We did the Laplace of dy dt, and from the past you should know that we have seen d squared, second derivatives. So in this case I want to see if we can figure out what dy dt is in terms of the Laplace transform, because those are the types of, just with the anticipation that those are the types of differential equations in second order that we've seen before, and see if we can figure out a pattern for higher order ones as well. Using the same logic we did before, let me go ahead and rewrite this one here. Remember that this Laplace of dy dt was s of big Y minus y of 0. Using the same kind of definition that we did before, you're going to say 0 to infinity e to the minus st times, I'm going to call this y double prime of t dt. Similarly, as we've seen, we say u is equal to e to the minus st, u prime equals negative s e to the minus st, v prime is equal to y double prime of t, and v is equal to y prime of t. We can carry out the same thing and we say this is equal to, well, u times v, which is going to be equal to y prime of t over e to the minus st, and that's going to be evaluated from 0 to infinity, minus integral 0 to infinity, e to the minus st. Oh, I missed something here. This integral winds up being u prime times v, so I wind up saying minus s e to the minus st times y prime of t dt. Focusing on this first term once again, this first term winds up being the limit as t goes to infinity of y prime of t over e to the, I think I messed up here, didn't I? E to the minus st. This should be a positive. Oh, I did. Yeah, when I multiply these two together, let me just back up and let me clarify here. This should have been u times v, which gives me the product of these two. I can rewrite this function in the denominator here, but the exponent must be positive now. So u prime, y prime of t over e to the st, and this is going to be minus y prime of 0 over, I'm going to go ahead and call this 1, because I know that e to the s times 0 is going to be e to the 0, which is just 1. Focusing once again on this term here, this is a y prime function, but this e to the this exponential function with t will wind up overpowering this numerator here as t goes to infinity, so this will wind up going to 0. And what we have left is this piece right here. And both of these terms come from this first term up here. So the next part winds up being plus an s, 0 to infinity, e to the minus st y prime of t dt. So I can continue this down here and say, well, this is going to wind up being s. This right here we've already established was the Laplace worked on before, which is Laplace for the dy dt function, or derivative. And that is actually written up here, so I can just take this and plug that into, or replace this integral with all of this here, because that's what this definition is defined as. So this winds up being this s and this s are the same one, times sy, big Y, minus y of 0. And then of course I have this first term sitting out here, which is minus y prime of 0. So this simplifies to s squared times a big Y minus s little y of 0 minus little y prime of 0. So if you see the pattern here, you can see, well, this is the Laplace transform on a first derivative. You get this. The Laplace transform on a second derivative gives you this. By following that same pattern, we can say we can kind of guess what the Laplace transform for a third derivative might be equal to, and if you follow the same pattern, it'll be equal to s cubed y minus s squared y of 0, little y of 0, minus s y prime of 0 minus y double prime of 0. And you can kind of continue the pattern on and on and on. Notice, I'll reemphasize, this is only for, this applies for a function where we have y as with one independent, or I should say one input variable. This is important to, this is how this works for these kinds of functions, these kinds of transforms. Now for doing partial derivatives, the Laplace transforms and partial derivatives, the pattern winds up being very similar to this. But I want to save that discussion for class and actually go through the process of how that might work and see what the pattern is like in terms of the relationship and how it's very similar, the similarities to this one as well. So there you go. There's the this talks about the pattern. Hopefully you should be able to tell me what a Laplace transform on a fourth order, say something like that. You should be able to tell me what the pattern of that's going to be based on what we've already shown up here. Once again, Laplace for first order, Laplace for second order winds up giving you this, and based on that we can go ahead and continue the pattern and for any order. So hopefully that'll help, and I'll give you some practice problems to do in the next lesson, and we'll hopefully be able to discuss a little more in detail as to how this is used, and try to refine that. So until now, good night, and we will see you on the next lesson.